Many engineers believe that because current transformers cannot be dual accuracy class, voltage transformers also cannot be dual accuracy class. After all, if a CT cannot combine 0.2 and 5P accuracy class on one core, then how can a VT combine 0.2 and 3P on one winding? It sounds logical, right? But it's not true. To see why this belief is wrong, we must understand the difference between CTs and VTs. So first, let's understand why CTs cannot be dual accuracy class. According to IEC 61869 Part 2, a metering class CT with instrument safety factor 10 must maintain accuracy within limits for 25 to 100% of rated burden, 5% to 120% of rated current, and must saturate early, below 10 times rated current, to protect meters during faults. On the other hand, a protection class CT with accuracy limit factor 20 must meet its specified accuracy limits for 100% of rated burden, and must not saturate up to 20 times rated current during faults. So the metering core demands early saturation, while the protection core demands no saturation up to very high current. These two conditions cannot be satisfied by the same CT core. That is why dual accuracy class like 0.2 and 5P is not possible on one CT core. Now that CT behavior is clear, let's move to the opposite case, VTs, and understand why VTs can be dual accuracy class. According to IEC 61869 Part 3, a metering class VT must maintain accuracy within limits for 25 to 100% of rated burden, 80 to 120% of rated voltage. And a protection class VT must satisfy accuracy limits for 25 to 100% of rated burden, 5 to 190% of rated voltage for systems where the neutral is not solidly earthed, or 5 to 150% of rated voltage for systems with solidly earthed neutral. Here's the key insight: the two accuracy requirements do not contradict each other. Protection class does not conflict with metering class, it extends the voltage accuracy band. And that is why VTs can be dual accuracy, for example 0.2 and 3P, which means metering accuracy is fulfilled for 80 to 120% of rated voltage. And additionally, protection accuracy and transient response are fulfilled between 5 to 80% and 120 to 190% of rated voltage. At this point, you might be thinking, why should we specify a dual accuracy class VT, when separate accuracy class VTs can be applied? Let me show you how this exact misconception has caused nuisance tripping in a power plant. A generator at 22 kV had a VT with two secondary windings. One winding was designed for class 0.2 feeding the AVR. The other winding was designed for class 3P feeding the protection relay. During a routine test, the AVR setpoint was increased to 105%, perfectly within generator capability. When the machine reached about 22.9 kV, it tripped on overflux protection. The fault record showed the protection relay saw 23.3 kV. The first reaction on site was predictable. Something must be wrong with the relay. Then the suspicion moved to the AVR. Then to the PT ratio. Then to wiring. Everything was healthy. The real problem was hidden behind a simple misconception: the belief that dual accuracy VTs can't exist. In this case, the AVR read voltage accurately with the 0.2 class VT. But the protection relay misread it due to the large error of the 3P class VT. So, if your project uses VTs for AVR, generator protection, sync check, and metering, then the VT must be specified as dual accuracy class. Otherwise, one device will read correctly, and the other will misread the generator voltage and trip. Stop applying CT logic to VTs. Always specify dual accuracy class VTs in generator circuits. This single specification shift can prevent false trips, unnecessary shutdowns, and contractual disputes. Thank you for watching.